Today our objective is to redesign the swimming pool so that it holds the maximum possible amount of water while using exactly the same amount of construction material as the real pool.
So we know that the real volume equals 1782.919 cubic meters. And
this means that the total surface area of concrete, the floor, and the four walls must remain constant, and this fixed surface area will be our constraint in the optimization process.
Now I'm going to talk about the areas. We need to have three things in mind. Number one, the length is 50.03, the width is 21, and the average depth is 1.69 square meters. For the first area, this value shows the concrete used in the pool, but it cannot be changed in our redesign.
Surface area of the floor and the wall is fixed, and the only thing we're allowed to change is the shape of the pool. We chose a rectangular pool model. We defined the following variables. Okay, so first we used H, L, and W as our variable for depth, length, and width. To get the total area, we add our different areas. For example, this is the area of the bottom of the floor, and is the long side walls, and this is the front and back walls. And for the volume, we multiply depth, length, and width, as we already know. And now to start with our optimization, we isolated H to get our average depth, because as you may know, the bottom of our pool is not flat. Okay, so here's our equation for the area of the floor, for the area of both walls, and we got this. This area is all the materials we can use. Now, okay, so this is another way to get the equation of the area, and this is the area, and we want to maximize volume. So there are two equations to get the volume. We saw them in class, and they are for rectangular shapes. And so in here, to start, we isolated y, and we got this equation, and then this isolation, we put it in our other equation for volume. Sorry, this is one is for volume, this one is for area. And we got this. This is now our equation. Okay, so now we derivated our equation, and this is our result. And we isolated x to get our critical point. And we use the second derivative test to know if it's a local maximum or minimum. Since it's less than 0, we can assume it's a local maximum. Okay, so now in the isolation of x, we use the real values to know that x equals 20.75. And if we isolated y and put the real values, we can know it's 10.38 meters. Okay, so our new length is this number, and width 2 since we used this equation, and our new depth is 10 meters. Last but not least, our new optimized volume equals the multiplication of all our sides, and this is our new optimized volume, and we can divide it by the change of our optimized volume minus our real volume, to know that our model is 2.5 times faster. Okay, so basically, after optimizing the pool using calculus, the volume increases, even though the construction area stays the same. This happens because we changed only the proportions of the pool, not the material. The key geometric decision was finding the best balance between the base and depth using derivatives. A limitation of the model is that it is only mathematical and does not include real construction factors. The model is idealized, and a depth like that is not good for swimming, but it is still useful because it shows how optimization can improve real designs.
In phase number 1, I learned to identify key variables and establish the function with the context given. In phase number 2, I applied the rules of differentiation to find extreme values of the function. And last, in phase number 3, I learned to apply optimization techniques. The part that helped me the most to understand derivatives, I think, was phase number 2, specifically calculating the first derivative and setting it equal to 0. The project directly connects to real-world optimization problems, such as maximizing the volume of a box with a limited amount of material.
Well, in phase 1, I learned how to model the real pool and calculate its surface area. In phase 2, I learned how the derivatives describe how fast the water level changes. And in phase 3, I learned how to use optimization to maximize volume with a fixed surface area. I think phase 2 helped me better because I saw the derivatives as our real rates of change. And this relates to real life because it relates to how pools and containers are designed and how calculate explains real changes like filling or draining.
On the first part, I learned how to take the measures of the pool. On the second was to learn how much the pool was going to be filled. And on the last one was to use the derivative to take the formula so we get a model with the same amount of materials, but with like improving it. I think that the part that helped me understand more derivatives was the last one.
Okay, so in phase 1, we calculated the total volume of the school swimming pool. That was the moment when I really understood what derivatives represent because I started to see them as curves that describe how things change. In phase 2, we analyzed how fast the pool was filling and emptying using rates of change. In phase 3, I did most of the optimization calculations, and honestly, I found them fun. This project connects to real life because optimization is used in constructions to design better spaces, and even in medicine, it is useful to analyze changes and find optimal solutions.